Hello? Yes, you can hear me. So good morning, everybody. We are glad to see that the crowd is growing. Hello, welcome to this session, which is dedicated, the first of the two sessions that are dedicated to the fuel cells and hydrogen. That's correct. You're not in the wrong room, and this is indeed still the Road Transport Research Conference. So welcome back for the second day. And my name is Pietro Caloprisco. I'm a project officer at the CleanHydrogen joint undertaking. And together with Roland, we will be moderating then this session, which is dedicated to the low TRL projects in fuel cells and hydrogen transport applications. Now, I understand that this is the first year actually that this technology is admitted to this conference, and we are really glad. And I think it's also a testimony of the maturity that we have reached. The first joint undertaking started already in 2007. And since then, we can see the huge progress that we have made. And I think this is particularly visible in transport. Back in the days, the focus was really on light-duty vehicles, material handling vehicles, then we moved on to buses. Then over the years, we have seen an increase in the performance of all the components, the technology, the fuel cell systems, and we have seen also the cost decrease. So now it only makes sense that fuel cells and hydrogen are considered as an option, a mainstream option for the decarbonization of heavy-duty application, waterborne, aviation, trains, and what we are going to talk about today, especially, it's road heavy-duty applications. So from the technology point of view, there has been this progress in a very broad way, and then we will hear some more about the details. And I think it's also interesting just to mention very briefly that this also had the impact beside the real world, also here in Brussels, in the way we operate. So in the past, I mentioned we had the first joint undertaking, and we were the only outfit that was solely dedicated to the development and the deployment of fuel cells and hydrogen applications. As the technology started to mature, we are starting to cooperate more and more with the additional organizations. So you will see joint undertakings such as Clean Aviations or Europe Rails that they were not really dealing with the fuel cells and hydrogen in the past. Now we are starting to cooperate with them. And the same goes with the 2.0. And the idea is really that we are avoid overlaps and that we are really going in the same direction, aiming in the same direction. And if you want to understand broadly how we can cooperate, also maybe when you're looking for funding, as a rough guideline, you can imagine the following. We, in our joint undertaking, we are looking at the building blocks, the development of the fuel cell system and all its key components, while the other joint undertaking, the other organization are more looking, let's say, at the development of the vehicles. And so the idea is then to merge the results, the outcomes of what our programs are doing. So this morning, we have two sessions dedicated to this technology. And the first one is going to look more, I would say, on the low TRL side. And we will start with 3 projects. And I was told not to anticipate too much about them, not to spoil the surprise. And just 2 reminders. So one for the speakers. I was several times told by the organizer, you have to stick to 15 minutes. So it's not coming from me, but I will have to be sharp on that one. And for the audience, please hold your questions until the end. We will have the Q&A at the end. We should have sufficient time for then having a discussion about the technology. And last but not least, also during the coffee breaks, remember to go downstairs. There is a little bit of an exhibition where you can get additional information about technologies and other events. And with that out of the way, I would like then to invite the first speaker, Johannes. Johannes has 10 years of experience in the sector already. He's a mechanical engineer by formation. He's working in the AVL on research, project acquisition, and project management. And he's also the coordinator of one of the joint undertaking projects, MORELife. Johannes, please come here and tell us more about the project.
Thank you, Peter. So, good morning, everybody. Thank you for the nice introduction. Thank you for having me here. I was reminded that I have to speak into the microphone. So, MORELife. It's about durability, it's about decreasing costs, and it's about optimization, the lifetime of a fuel cell application in heavy duty, in the heavy duty fields. So a rough project key facts. So we have 7 partners involved. We are from around 4 countries. So it's NetStack, EKPO, Technical University of Munich, Mebius, University of Ljubljana, AVL, and Technical University of Eindhoven. We have a rough budget of 3.5 million. Which is 100% funded thanks to the CleanHydrogen and the EU. We have rough person months, and the project already started in 2021, and we are about to have a little extension of the project, and we are aiming to have to end the project by beginning of 2025. So about our core objectives, as I said, it's all about durability, it's all about costs, and also the implementation of the fuel cell technology in the heavy-duty sector. And therefore, some specific tasks need to be triggered. We have to figure out how we can accelerate it, how we can perform accelerated stress tests to do a lifetime verification. We do a specific improvements on the core components of the fuel cell, so-called the catalyst layer. We, in parallel, also we try to improve degradation models, which is a key component, I would say. And for sure, resulting out of these points, we will try to optimize and to validate the operating conditions of the fuel cell, and in the end, doing a full fuel cell lifetime indication. So this is basically the story of our project. And now I really want to focus on the results that we have gained so far. Because this is the focus of this conference, as I've heard. And as I said, it's about also the understanding of how can we endure and how can we make the fuel cell more durable. And this is strongly related to the understanding of how a fuel cell ages. And at the end, we investigated strongly the effects of this degradation. And because of that, we were lucky to have fleet data in our consortium that we could, so to say, apply on specific accelerated stress tests, which was then created by the Technical University of Munich. And we figured out that 3 specific accelerated stress tests are the most severe in aging the fuel cell. And this is, we dedicated then the so-called voltage cycling, the startup and mitigated shutdown, and the load and humidity cycling on the fuel cell. With these test protocols and these tests performed by TU Munich, we then feed it, so to say, our models, our performance models, which were then improved, so to say. And in parallel, this was, so to say, good input for the creation of our catalyst development. And with a feedback loop from our catalyst manufacturer, also the extension of the model was being done in terms of degradation of, so to say, bimetallic catalysts. In our project, we are aiming to have a specific bimetallic alloy, a platinum copper alloy, which hopefully allows us to gain or to create a cheaper catalyst material and a catalyst material with high durability. So again, we have then created these models, adapted them, And at the end, but we are not that far, we want to perform also durability tests and do a lifetime assessment on these models and also of the material. So just an example how these so to say accelerated stress tests are being performed. It's not so easy to translate a specific profile, a speed or a load profile into a specific stack load cycle. And for that, we approached we took the existing vector tool using the speed profile of this tool. Then we considered 4 specific profiles: urban, rural, highway, and a climb profile, and translated them because we have a system that is current controlled, and we try to converge this into voltage control into the fuel cell. And this is what we then created. We defined, so to say, AST matrix with an upper potential level of 0.5 volts and roughly 200 K cycles. So this is just an example of one of the accelerated stress tests we created, one of the 3. Okay, but also mentioning then in parallel the model framework which has been performed. So the idea of these models, or the need of these models is, as I said, a deep understanding of the degradation. Also having an extension of these models to our needs of a degradation of a bimetallic catalyst. So this was not existing yet. We do have some experience in, or we do have some models for pure platinum catalysts, but in terms of bimetallic, we didn't have it anyway. So the idea is really we had to apply, or we had to adapt these models in specific dissolution processes which happens in these catalysts. I don't want to go into in depth with that because it's really a deep electrochemistry. But at the end, the severe or the most significant so to say issues we have with this bimetallic catalyst is that the copper is dissoluting over time and is somehow poisoning the fuel cell. And this is what we want to investigate. This is what we want to mitigate at the end. And therefore we created these models which shows the process of these dissolutions. And these models could have been parameterized and are now working accordingly. Okay. Yes. And another interesting result what we have is also, as I said, the work on the catalyst material itself. So we in total we had 3 generations of catalysts, and what you can see here is the 2nd generation of the catalyst. We kind of applied a specific test on this catalyst. It was not recording or in regards to the created accelerated stress test, but this was a more severe one because we wanted to have results at the end of life of the material. And on the left side, you can see a so-called polymerization curve, which is an indication of the performance of a fuel cell. And you can see on the red dotted line, so to say, where at the beginning of the tests we could see a really good performance. So the performance at the beginning of test was quite significantly good, but over time there was a drop of performance, and we could see a so-called, as I mentioned, an anode poisoning due to the dissolution of the copper. But here's an interesting thing. We then tried to investigate how much copper was on the surface of the anode, and we then performed a so-called cyclic voltammetry to investigate this. And after the first cycle, we could see that this is hard to explain, but anyway, it's kind of doing an investigation, but also seeing that the copper was in the first round of, let me check this, sorry, of this cycle was vanished, so to say, and we could have seen a regain of the performance of this material. So this was really an interesting fact. But at the end, we have some indications that we should definitely or dramatically lower the copper content in our catalyst. So we are now in the stage of having a third generation. We tried to improve this material in terms of all the investigations we did on the second generation, and try to sort of resolve these problems. And I don't have these results now here of the third generation, but we can see that the last generation is really performing well. We don't have the durability tests yet, but we are kind of hopeful that this works out also in terms of durability and in the stability of the catalyst itself. So this is a significant point. Okay. We also have some, this is about the results. We also have some ongoing collaborations between other research projects. So more specifically, MORELife is in discussion with the RWTH project. It's also a road transport heavy-duty application project. And we try to provide some of these test protocols, what we have created, to the RWTH project. And once they performed these tests, hopefully we can get some results also in time, because MORELife is coming to an end and provides also the results for us that we can use then for adapting our models, for example. And also recently the MORELife project joined the so-called IEVETO cluster. Hi, Anje. So this is a consortium of fuel cell or battery-related projects, where we have, so to say, we search for some synergies we can find within the projects, and we also try to have a common dissemination activities. For example, we will have a joint booth at the TRA in Dublin. Okay, so about the impacts, we already have one actual impact, which I'm really proud of, what I'm going to show. Our MEA manufacturer, it's a small company, it's an SME, and during the project it was possible that we have created, or we have allowed them to ramp up the production of their MEAs. And also in terms of employees, we had an increase of employees in a period of only 4 months. And there was an expansion of their facility, which you can see on the right-hand side. So this is the midterm impact, or the actual impact, and now we are aiming to the impacts of 2023. So basically, we really want to, as I said in the beginning, to bring the fuel cell technology into the market, and this can only be done when you have severe cost reductions and a severe increase of the durability of the technology itself. And for sure, we have to do the industrialization of the product. So this is a really important thing. And so as I said, the targeted impact is then strengthen also the European fuel cell industry. And what we are also trying to do is to increase the collaboration between the academia and the industry. And so these are our settled goals, our impacts for 2023. And with that, I think I was able to manage it in time. And for more live questions, please contact me. And try to visit our homepage. It's morelife-info.eu. And thank you.
Thank you very much, Johannes. Very interesting. Thank you also for sticking to the time. So we remain still in the field of the durability of fuel cells with this very evocative name of the project IMMORTAL. And I would like now to invite Deborah Jones, who is the coordinator, to take the floor. Deborah, she's the director of research at CNRS. She has been the co-author of more than 250 publications in the sector, as well the inventor of 17 patents related still to fuel cells and electrolyzer materials. And she has also a very strong experience as coordinator of projects at the joint undertaking. So please, Deborah, tell us more about the IMMORTAL project.
That's what I'm going to do. Thank you very much, Pietro. So good morning, everybody, and thank you for the introduction. Thank you to the organizers for inviting IMMORTAL to come and present this morning. So I'm going to be talking about the IMMORTAL project, improved lifetime stacks for heavy-duty trucks through ultra-durable components. So the project has now been going for just over 3 years. We have another month or two to run before the end of the project. So let me give you an overview of the overall project presentation with its partners, ourselves, CNRS, a national research organization in France, other research partners at IMTech, University of Freiburg, and then industrial partners, Johnson Matthey Bosch, FPT Industrial, and AVL, and Protexo is in charge of communication activities on the project. So we responded to the call for proposals in 2020. We started at the beginning of 2021. We're actually a 42-month project now, so we're 95% finished, whatever that turns out to be. 3.8 contribution in terms of funding from the CleanHydrogen JU. So we're talking about heavy-duty transport application. Obviously, the key requirements are high efficiency and durability, and so I've expressed those. I don't know if we have a pointer here. If that works. Express those here. So the target in terms of performance in the call for proposals was to reach 1.2 watts per square centimetre at 6.75 volts. The 1.2 watts per square centimetre is not in itself a massive issue. It's lower than we had worked on previously, or the targets in previous automotive light-duty vehicle projects, such as Inspire Volumetric or Gaia, where the performance target in terms of power density was 1.5 or even 1.8 watts per square centimetre. But the point is that it's at a higher voltage because we're looking for higher efficiency. So that actually then is this point here. So this is one of the polarization curves that we obtained in the framework of the Inspire project. You can see that IMMORTAL beginning of life target is just above, in fact, that polarization curve there at the current density of 1.78 amps per square centimetre. So that to say that it was beyond the state of the art at the beginning of the project. In terms of the lifetime, the target in the call for proposals was actually 30,000 hours. That was actually beyond the SRIA target, which was developed subsequently, which was 20,000 hours for 2024, so 30,000 hours. If we look at that beginning of life target then on the right-hand side, then here, that's a beginning of life target. And if we say that 10% degradation then represents the lifetime, take 10% off of that voltage there, and then our end of life voltage is going to be 0.608 volts at that current density, which gives an average decay rate of only 2 microvolts per hour. So that's obviously a very low degradation rate. So beyond state-of-the-art performance and a very low degradation rate are our challenges. So how do we go about this? By having an extremely highly performing consortium, I must say. All partners interacted extremely well together, lots and lots of collaboration. But these are the main pillars then of the activity from left to right. So developing load profile tests, I'm going to be calling LPT for heavy duty MEA in particular, performance and durability assessment. We have to develop those MEAs, so we need components that are specifically designed for high durability and high performance. That's the second block. And then we validate those then using these accelerated stress test and load profile test protocols. Equally, there was no intention ever to actually test out to 30,000 hours of operation. So on the basis of what we could derive from the degradation profiles using AST and LPT protocols, then to develop algorithms for lifetime prediction to see to what extent we would actually achieve 30,000 hours of operation. And ultimately, of course, to achieve the targets in terms of performance and efficiency in particular, but also a calculation on the cost. So we have some of the main milestones that are indicated there as the blue spots along the bottom. So let me show you some of the results that we've attained during the course of the project. I'll be talking just a little bit about some of the components, the catalyst and the membrane. I'll talk about the CCM, I'll talk about the lifetime prediction, and where we are overall in terms of the performance. So here's one slide on development at Johnson Matthey on de-alloyed platinum cobalt catalyst supported on carbons. I'm not going to go into any details of the preparation, but I just want to point out that Johnson Matthey developed a whole range of different carbons, of different catalysts, and with the platinum cobalt actually supported on these different carbons, with some of the specifics given there. And in the testing carried out, this is on 50 square centimeter cells, the platinum cobalt, whether on air or oxygen, simply for calculation of the mass activity, but you can see they're more highly performing both at low and high current densities than the standard platinum on carbon material. Moving on to the membrane. So the membrane uses a nanofiber development, a nanofiber web that we've developed in our labs at CNRS is now scaled up. This is showing an accelerated stress test on one of these membranes. You can see it's scaled up here. So this is the composite membrane containing the PFSA ionomer, containing the nanofiber web reinforcement. It's a 10 micron membrane. What I'm showing here at the top is the OCV degradation, and at the bottom showing essentially the gas crossover. So it's the response to a small pressure differential at the anode. So the accelerated stress test is the cell is being held at 90 degrees C. There's a wet-dry cycling at open circuit voltage hold. So we're testing both for mechanical and chemical stability of that membrane as it's being held in the membrane electrode assembly. So this is the reference MEA with the absolutely same construction, but a different kind of reinforcement, standard PTFE reinforcement. This is the IMMORTAL membrane with a nanofiber type, non-PFSA, non-fluorinated reinforcement. And in fact, we stopped the test here, or Johnson Matthey stopped the test here at 120,000 of these AST cycles, which actually corresponds to, in real life, more than 2,000 hours of actual AST testing with no rupture failure. We can see that there's a bit of a thinning here. You can see that through the drop in the OCV, but there's no catastrophic failure. The membrane is holding out. It's also interesting to see that for membranes of exactly the same thickness, that we're also using less reinforcement material with the nanofiber reinforcement than in the case of the PTFE reinforcement. So how does that all come together then in terms of the CCM and the performance in the fuel cell? So here we have results from the testing at Johnson Matthey and at Bosch. We have three essentially generations of CCM or membrane electrode assembly. This was our baseline. This was generation 1. This was generation 2. This is in terms of the power density at that 1.78 amps per square centimeter spot. So you can see that we've been gradually improving in terms of the performance. But notably as well, Johnson Matthey has been using far less platinum. There's been a lot of platinum thrifting, so improvement with regard to the amount of platinum and in fact generally noble metals that are incorporated into those CCMs. So going down from 0.84 grams of platinum per kilowatt down to 0.36. So that's a significant improvement. So that's what's written up there. These CCMs were tested in both short subscale, so small single cells or single cells, 50 square centimeters, but also full size short stacks for a total of, in fact, over 7,000 hours, once again, without any catastrophic failure. So let me show you that. But first, let me tell you all about the load profile test development. So important work that was done on actually what is the load profile that we use to actually test these CCMs that we've developed. So we're talking about truck activity, truck usage, obviously many different kinds of profiles that could be used for that. Our original intention was actually to use real-life data from fuel cell trucks. That actually wasn't possible during the course of the project. But it was possible at FPT to have real-life mission profiles from different kinds of trucks. And that work was to simulate different drive cycles. In fact, more than 450 drive cycles were actually simulated. And then the extraction of the stat load profiles and the selection of the load profiles from testing, a lot of work between FPT and Bosch. Those load profiles were then processed to enable their usage actually in terms of a modal load profile test that we could actually use for testing our stack. In parallel, there's the work done in collaboration between Bosch and IMTech on accelerated stress testing on single cells, load profile testing on single cells, on short stacks as well for AST and LPT. So that gives us the acceleration factor in terms of between the AST and the LPT, but also the scaling between what happens in a single cell and what happens in a stack. So with application of all of that, and I've already told you that in total there were more than 7,000 hours of load profile testing then carried out on different generations of short stacks. We used an initial load profile test on our baseline MEAs and also on our Gen 1 MEAs. We then used that improved load profile test that I've just told you about to test subsequent generations of MEAs. But the message here really is that in total, more than 7,000 hours of testing, 2 different sets of stack hardware, in fact, Bosch stack hardware, but also AVL stack hardware, and these initial and improved LPT protocols. This shows you here then the improvements during the course of the lifetime at that 1.78 amps per square centimeter point, moving up from the baseline up to generation 1 is the green line there, and the ultimate target point, which is that one there. So all of this AST and LPT testing, of course, generates a lot of data. What we discovered was that the degradation is essentially due to platinum dissolution, loss of the electrochemical surface area of the catalyst. So that was determined experimentally. That was also modeled. And using this information and following the development then of lifetime prediction algorithms, the work done at Bosch was actually able, first of all, to model the baseline voltage loss here, using having used then all of the information on the ECSA loss actually determined during the AST experiments. And then I mentioned earlier on that our criterion is to achieve only, let's say, or maintain 90% of the voltage at 1.78 amps per square centimeter, and extending that lifetime prediction out to 30,000 hours does actually show that in principle that would be obtained. So that's a very interesting result that's obtained actually with the baseline MEA with the baseline MEAs, that they would actually achieve the full 30,000 hours were we actually to test out for that period of time. So this summarizes really what we've done. I've talked about the new membrane architecture with this novel reinforcement, thin membranes, 10 micron membranes that allow a very high durability, no rupture failure, high mass activity alloy catalysts developed on novel carbons that certainly show an increase in the beginning of life performance on the MEAs. Very significant PGM thrifting, so reducing the amount of platinum and other PGMs included in the MEAs, reducing the amount of PGMs by more than a half, by more than a factor 2, let's say, is a better way of saying. Several short stack iterations, actually integrating the new materials. It's often difficult to do that within the framework of the period of a project. Time goes by very quickly, but we were able to do that quite successfully to prepare these different short stacks. And then obviously extremely important was all of the end-of-life testing on the baseline MEAs, actually to show what was the problem with regard to degradation, to feed that into the algorithms that I've talked about, but also to improve materials. important work done on developing these load profile test protocols, because we need to know what are the relevant conditions actually for testing our single cells and our stacks, and then bringing all of these results together for the lifetime prediction. So there are remaining gaps. Perhaps I'll add 2 remaining gaps into what's written up there. So certainly a gap actually in being able to use real-life data from fuel cell trucks that we can use then to actually validate our experimental results. That's missing. I think we also need to know to what extent the management system is going to influence the lifetime of the CCMs that we have. So the size of the battery, the voltage limits and so on are also important factors, gaps that are missing at the present time. What we showed is that with our baseline MEA, that in principle we can reach the lifetime target of 30,000 hours. Those are not the most performing, highly performing, that fall short by about 30 millivolts at the 1.78 watts amps per square centimeter point. So they fall short a little bit. They would achieve the lifetime. On the other hand, we can achieve the power density targets with alloy catalysts, but then on that side, the durability is not achieved. So a gap in actually achieving both the beginning of life power density and also the durability at the same time. But I think having, in principle, achieved the lifetime with an immortal MEA is a very significant result. And I think longer term as well, there's clearly going to be a challenge to close the durability and performance gap if we're moving on to fluorine-free MEAs. So the project partners will use the results in various ways. CNRS, GM and Bosch are continuing to work together on materials developments in the framework of the Highlander project. JM is going to move forward with the use of these components in their new MEA products. There's been a lot of methodology development and simulation methodology development. So methodology standardization for LPT development at Bosch, simulation methodology and lifetime prediction tools at FPT. Yeah, I think I've just about been through that one. So lots of application areas, both for the research partners and for the industrial partners. And finally, just to mention that we responded at the beginning to invitation from Mission Innovation to actually interact with a project in the United States, a million-mile fuel cell truck project. We have regular 2 monthly meetings actually with that grouping that generally gathers around about 60 different participants from the US, from Japan, and from Europe, who are all working on fuel cell truck heavy-duty applications generally. And so thank you.
Thank you very much, Deborah. Very interesting and encouraging results. So I would like now to move on with the third speaker. We are changing a little bit the topic, the subject, and Federico Zenit, who is a senior researcher scientist at SINTEF. He has more than 20 years of experience in the field, and his night job is to be the coordinator of the joint undertaking projects, and one of them is StasHH, and we're looking forward to hear about it. Please, Federico.
Thank you very much, Pietro, for the introduction. Yes, we started a project MORELife and then IMMORTAL, and we discussed with my colleagues, but maybe a project should have a name of like coffin or something. But I'm going to be talking about boxes in a few slides. But it's actually about standard. We are not really that low TRL in this project. So for the overall presentation, it's a pretty big consortium we have in this project. Budget is pretty respectable, over 14 million euros. At the center we have several research institutions, mine own SINTEF in Norway, and FEV in Germany, TNO in Netherlands, CA in France, and Waterstofnet, which is the Hydrogen Association of Benelux. And then we have OEM side representing buses, construction equipment, trucks, ships, inland ships, ocean-going ships, automotive powertrains, and trains. So we got pretty much everything moving on the surface. So then we have several names for fuel cell manufacturers. We got most of the industry, I would dare say. So Novair Intelligent Energy, Plasticom used to be known as Aaron Klinger, and as Fronius, Freudenberg, Protomotor, Toyota, and Ballard. and this is consortium. Then we also have external observers, so you can see this is getting pretty crowded. You got very well-known names like Airbus, Bosch, Hyundai, and so behind Cellcentric is also Daimler, in addition to Volvo again, so crowded. So what are all these people doing? Is working towards a standard will kickstart fuel cells in the heavy-duty sector. And why do we want a standard? Well, the main reason behind the concept of having a standard was that one of our partners, VDL, had to rebuild their buses several times over every time they got a new stack from their vendors. And they were getting quite tired of that because they had to rebuild the chassis every time. So I said, let's have a fixed size, and then why not standardize everything we need to standardize? The idea is then to pool several of these markets. When you are building light-duty vehicles like cars, you can, if you are a successful car, you can build millions of it. But that's not the case for heavy duty. You're not going to build millions of trucks or ships. So the markets are necessarily going to be smaller. But if you pull them together, building all the same kind of system, then you can still achieve economies of scale, which means it's easier to achieve automation, which then will start a positive feedback loop with even greater economies of scale. These will also allow competition among fuel cell manufacturers, because best example I have is the deal Alstom had with Hydrogenics a few years back to make their trains. Then you have the engineers of Hydrogenics, the engineers of Alstom working together for several years and building a system. Then it's very difficult if one day Alstom wants to buy their fuel cells from Ballard, the Proton Motor, whoever else, to just replace them, because then they would need to decouple themselves from a system. Instead, if we have a standard, it's a lot easier if your vendor is bought by some hostile company or simply decides to go another way to buy from some other supplier. These will also increase their ability in supply chain. If your fuel cell breaks, you take it out with the one system, plug in another system. That's all. And all this will then have the incentive from a economic point of view for end users. It's going to be easier for them to operate fuel cells. It's going to be cheaper. It's going to be easier to maintain. But it's also going to be easier for OEMs to go into fuel cells. Before, you had to get all your engineers together with engineers of the fuel cell supplier and work with them for years, possibly. Now you simply know where what the interface is, where the line goes, and that's what you have to provide. And eventually, these will allow to scale these to, well, the project has a target to 1 megawatt, but in principle, it doesn't need to stop there. And this way, then again, you come back to the market pooling. So, what have we achieved? I promised boxes, here they are. So we have the first size format standard is the most critical for OEMs. This is really important. If the next fuel cell it does not fit the previous hole you had in the previous chassis, then you have to rebuild the chassis, and then you start going down to a rabbit hole of recertification, homologation, and a process that can take years. So you want the things to fit where they're supposed to. We ended up with these 3 base cuboid shapes, A, B, and C. We photo over every millimeter in here. We start with a basic unit of 340 millimeters, which represent the height of this cuboid. Then the width is little more than 2. That's because somebody really wanted last 2 centimeters. So we thought about this much. That's how hard it was. So it's 700 millimeters wide. And then the lengths are 3, 4, and 5 times the basic unit. And that defines A, B, and C. Of course, there is no D because that would simply be 2 A's in a row. Also, there's a standard by which if you double the letter, it means that you're stacking upwards. So there's double A, double B, triple B, which are popular sizes for now. So AB, AA, and BB are popular because they fit exactly in the place of fuel tanks in European trucks, and the triple B in the engine bay of European trucks. European trucks are very important because they're a very large market and they're very compact, especially compared to American trucks. So that's why a lot of the standard come from there. Then, the physical interface. You want also to standardize where hydrogen is coming in, where air is coming in, where the coolant is coming in and out. And in general, neither OEMs nor fuel cell manufacturers were interested in having a specific point with a specific connector. They were much more concerned in having a general area. It's pretty easy to move a pipe of a few centimeters. What is difficult if the pipe has to go all the way around the box. That would be a problem. There are some exceptions. For the most important exception is power. Doesn't matter, power cable you can bend around, but what is really important is where the hydrogen is coming in and out, air and coolant. Then, third part of 3, digital interface. This is defined on top of CAN bus, but it's also implementable over Ethernet, and it was actually the maritime OEMs who were more interested in Ethernet. Automotive were happy with CAN. Signals are defined according to existing standard, SAE J in 1939. We actually contact SAE, we are in dialogue with them to include our modifications to the standard, more than modifications, additions. The state machine is not too complicated, represented there, and there is also a possibility of having a hierarchy of fuel cell modules. That's more important, especially for maritime and trains, large applications. And you can have all of them managed by a single controller, or you can have one of them acting as a leader on followers. Again, we don't have a specific connector, just like for the physical interfaces. It needs to have 18 pins, but that's all the requirements. Pretty easy in a workshop to change whatever connector you have. And then, well, of course, a lot of EU project defined standards. The problem was that then after defining a standard, that was just a bunch of papers. So they required us this, and that's why we have a bigger budget. They required us to start building these prototypes to prove that we actually can do it. We're going to build 8. There have been some deviations from the standard, mostly because the standard during the project has been a moving target, and so we have had some tolerance, but all fuel cell manufacturers are going to provide final designs, and they will be public, and you will be able in 1 year from now to go up to them and say, I want this one for my project. Most popular sizes, we have seen a AA and B. We haven't seen a BBB yet, and we haven't seen a C, even though the C size was supposed to be popular with buses to be installed on roofs, but apparently B is just as good. The most popular power level is about 100 kilowatts, so in a higher range. Some are down to 36, some up to 125. These modules all include the air compressor, hydrogen recycling, all the coolant pumps, control module and exhaust. They don't include, of course, the hydrogen storage, that's somewhere else, and the air filters and the heat sinks. And the DC-DC converter may or may not be inside. We had a lot of discussion whether the DC-DC had to be included or not. We concluded that it's something that it's better is not fixed in the standard. There are some cases where it's useful to have it when you have only one unit. If you, maritime especially, you don't want to have the DC inside because you're going to have a separate unit for that. Testing, yes, we have built this, and that truck runs in the Netherlands. This truck was also the Hydrogen Week in Brussels last year. It's a truck built by VDL with 2 separate A-sized units, built by Plasticom. You can see the logo. And then we have 2 testing rigs in the lower picture. Fortunately for intellectual property reasons, it's you cannot see the actual unit there, but these have not been deployed at CEA. We are going to start within, I think, next week, a new round of testings. Test protocols will be published. They're still waiting to clear that. And there will also be some on-field tests with a genset that VDL has decided to build. And also VDL has decided to extend this to SOFCs. We assume the PEM throughout, but actually this the same technology can be, the standard can be applied to SOFCs. So, impacts. Well, of course, in 1 year from now, you'll be able to ask this fuel cell manufacturer to provide you these modules with this standard. We'll also submit the standard to various bodies. We already in dialogue with SAE, and then we'll follow up with ISE ISO. We going to see then And we have a lot of FCM suppliers, of course. We have a representative section of OEMs, and so we have a significant starting market, and hopefully this market will expand. This will make it easier for OEMs to start developing their hydrogen vehicles, and they'll lower barriers for competition already in the short term. And ideally, these will give impetus to economies of scale, which means that in the longer term impact, well, we all know that heavy duty is more difficult to electrify than light duty with batteries. And hydrogen can solve this, but the hydrogen also needs scale. Batteries are piggybacking on the greatest infrastructure there ever was, the electric grid. Hydrogen does not have that. So we need scale in order to build this infrastructure. StasHH will achieve the melting pot of all these markets, and this will show then that zero emission heavy duty is feasible. That's not a pipe dream. And this then will hopefully encourage politicians to declare a year for zero emission heavy duty, just like they're all discussing about zero emission cars cut off dates. Norway is supposed to be next year, actually. We'll see how that's going to work out. Yeah, that was all for me. Thank you very much for your attention.
Okay, thanks for the presentation again, and I think we have sufficient time left for all the questions that may have come up during the presentations we had. Maybe to start the Q&A session, I have one initial question also regarding the StasHH project, because it was the last presentation we had. You proposed multiple box designs for the fuel cell systems. The first question that directly came to my mind when you were talking about the requirements, was there something regarding power density that was relevant for your design, let's say? So.
You cannot imagine how many times we discussed that, and eventually we decided to leave power density out. It's something that the fuel cell manufacturer will need to provide. Some applications require significant power density, some other not so much, like for example gensets. That very much depends what you're powering. So in short, no, it's not part of the standard.
Okay, thanks a lot. So maybe now I'll hand over to the audience. If there are some questions, just feel free to raise your hand, and then Xavier will hand over the microphone to you. Okay, so.
Sorry. I'll start off then. Simon Edwards from Ricardo. Just to follow up on that exact point about power density not being in there, I also saw in StasHH that you've not considered marine applications or large-scale marine applications. Is that correct?
No, we have them. Everything moving on the surface of the planet is included. We don't have planes, we don't have submarines.
Great. So if you needed a megawatt system and you followed your standardization mechanism, how much space compared to a bespoke system would you lose? Let's sort of ask it that way instead. That's a power density type of question. But if you're having to stack up 10 of your 100 kilowatt systems, how much bigger would it be than a bespoke system?
Well, not necessarily much bigger, but then again, we haven't run as projections. That's an interesting question. It remains to be seen how much is the pressure for you to have everything packed in neatly. So you can, when you have a maritime system with several, it's a very modular technology. So you want to be able to extract these modules and for maintenance. So you have to weigh several things. Yeah, I don't have a straight answer for that, I'm afraid.
Something to consider. Yeah, thank you.
Well, I guess we have the second question. Was that already answered with? Okay. So I'll give you. Okay, we have one in the front row.
Vincent Matalan from Toyota Motor Europe. I have a question for Deborah. During the testing, I assume you have used ultra-pure hydrogen, while in reality, when the trucks are driving, there could be impurities, maybe below the threshold from EN 17124. But was it also considered in your plan to test the systems at the threshold level of the EN standard of hydrogen purity?
No, I mean, that's obviously an excellent point, but it isn't something that was actually part of the scope of the work. Neither, in fact, within the call proposal originally, in fact, or something that we were able to do, in the project, but something that we'll have to handle in subsequent work, I think.
Okay, maybe I have a follow-up question regarding the more early TRL projects. So both of your projects had those load profile tests that you developed, and I think, well, for all of us being researchers, it's quite hard to get real driving data of fuel cell trucks, of course, but it's also difficult to get driving data of existing diesel trucks. So how did you handle that? I think in IMMORTAL you got at least some data for your simulation, but was that sufficient enough, or did you have to make some estimations for your profiles?
Yes, so we were very lucky in having FPT in the project, and so we were, in fact, in that part of the work, there was simulation of 450 different types of profile, so different types of trucks on different kinds of missions in different kinds of conditions. And from those, then we ultimately selected 4 that we thought would be most representative, and included those in the final modal load profile test that we used with different weightings. So we think that that it's obviously some kind of generalized load profile. It's not specific to any particular usage. But yeah, nevertheless was, I think, a step forward from the initial one that we were using. But clearly, yeah, I mean, it'd be very good, as I said, in one of the remaining gaps, actually, to have that data actually from fuel cell trucks with the particular mission, to enable to see actually how our materials and stacks and MEAs actually stand up with, under those real conditions. But yes, I mean, to respond to really reply to the question, then we did have access to actual mission data, and they were used as an important part of the work in improving our load profile testing.
Yeah, to add something, at least we were lucky to have EKPO on board, and due to the relations with the customers, we were able to get these profiles. Yeah.
Okay, maybe just one quick follow-up to that. And the impact of at least the 4 scenarios, for example, the IMMORTAL that you have for the stress tests in the end, did you see a huge impact on the different use cases for the cell durability, or is it like not really relevant which use case you actually pick in the end for the durability?
I'm sorry, I didn't quite catch the question.
So you said you had 450 different mission profiles.
Yes.
You selected, and from those 450 you picked 4 for the real tests of the fuel cells or the stacks that you had. And when I don't know if you have just piled those 4 and had them after each other, or did you have had a comparison of each individual stress test after one another?
Okay. So in fact, what we did was so we picked those 4, and then as I said, they were integrated into a modal LPT. So we had parts or we had each of those let's say profiles integrated with different weightings into our final LPT. So they weren't used individually, but collectively.
Yeah, thanks again. Okay, I think we have one question from Thilo.
Morning, thank you very much for the interesting presentation. I have a question to the both first project on the durability. Do you expect any impact on the lifetime and durability of the fuel cell stacks caused by vibrations, shocks, mechanical loadings?
Yeah, I mean, it's all I can answer is it's not something that we did. It's not something that we did in the project. Well, I think that the purpose of IMMORTAL really was to develop the components and try and show those components in functional and durable MEAs and in the stack under particular conditions. Then beyond that, it's once again the next step, I think, to actually to see to what extent the durability is affected by other effects.
Yeah, I understood that it was not covering it, but it was wanted to know your opinion if it becomes relevant or not.
Yeah. You want to continue the answer?
Actually, I don't think it's that important to have these mechanical stress tests on our material. No, so the answer is no.
Thanks.
Peter Braining, a question also to the StasHH project, kind of an outlook, maybe kind of lessons learned. Standardization of the modules as boxes is certainly helpful, but if we look at conventional powertrains, most of the standardization is in the if we say in the fuel cell world, balance of plant components, right? Like injectors or pumps or turbo blowers or whatever. So have you discussed in the consortium as a kind of a step also to have common parts like this, to have a similar approach as in conventional powertrain systems?
Yeah, thank you. It's an interesting question, that. And first off, in StasHH, we do not standardize the single BOP components because we decided early on that we would treat the fuel cell modules as a black box, and that's because we have all these competing companies in the consortium, and none of them want, of course, the others to have a peek at what they are doing. So whenever we move around these boxes, nobody's supposed to open them, and they're supposed to always be under the eyes of their own companies. That said, I think there is currently an open call of 3.1. So in CleanHydrogen undertaking. So if you're interested in that, I suggest start looking for partners.
I guess Simon has another good question.
Thank you, and thank you to all the speakers for answering all of these questions. My first question was a bit off-piste. It was on marine rather than on road transport. My next question is going to be a bit the same. Apologies about that. But in your considerations for lifetime, etc., did you include any aspects of the off-highway applications of these fuel cells in vehicles that are essentially on-highway vehicles that are modified for off-highway? Also, given the considerations that some people are proposing hydrogen internal combustion engines for that market because of the durability aspects, how do your fuel cells react and what are the prospects in the off-highway machine industry applications? Thank you.
Yeah, I mean, I can say that from a materials development point of view that there's a lot of work that would be directly applicable, of course, to fuel cells in other applications. So if we're talking about, we already showed in IMMORTAL that we think that we're achieving the 30,000 hours of operation under the particular conditions of the LPT that we were using there. So different test profiles and different objectives, of course, in terms of performance in different applications. But nevertheless, I think all of this learning on how to create, whether it's more durable MEAs or catalysts or catalyst layers or whatever it is, strictly applicable as well to other application areas, with then adjustments for specificities.
Maybe I can just add to that specifically with this course, maybe we were really looking at the MEA, we were really focusing on the durability, going to the materials, but then we have other courses in our programs which are complementing this knowledge. So for example, now we just started a project which is looking at the non-road mobile machineries, where we are really looking at the fuel cell system integration into excavator or shredders, machineries that we have not been dealing with normally. And in that case, for example, we are looking at the impact of dust, vibrations. So really the idea is to build these building blocks, put together the specific knowledge that we are getting here and there from the different projects. And then every once in a while we have the demo projects where we put them all together, as we had with Inspire in the past. So you take the best in class type of components, you see how they actually work together to make sure that the interaction between the different active components is going in the right direction. So maybe with MORELife and IMMORTAL, we didn't mean to, you know, like do the whole thing, but then we also transport mode types of projects which are more looking at the specific also demands, be that aviation, maritime, with the humid conditions. So at program level, we are trying to complement with all of these things.
Simon, and maybe as a clarification, maybe Pietro can say even more. Remember that the fuel cells joint undertaking is only focusing on fuel cells, of course. So, you know, maybe just for the audience, there is no possibility to fund anything which is related to internal combustion engine and hydrogen, because that's outside of the scope. And just to be clear, thanks.
Maybe one question regarding fuel cell degradation from someone who is not anymore as deep involved in fuel cell development, just more for sake of security. Purity of air and hydrogen, which means pollutants in both of the gases. To what extent? I mean, we have heard a lot about platinum degradation and copper or whatever, but on the gas side, to what extent? Or how critical is that today? Or is that with the hydrogen available, plant to be available, or the air filtering, is that solved, the issue, which was not in the past?
So what I can say, sorry, let me just jump in here. We have these, you know, these hydrogen standards used in fuel cells, right? And we didn't consider any real-time, so to say, environment impacts on the gas side, at least on the MORELife project. So this is what I cannot answer.
More question for Deborah, maybe on the very chemical, deep chemical side.
Okay. Yeah, you know, once again, similar question to the question from a colleague in the front from Toyota, and we didn't do it in IMMORTAL. It wasn't part of the project, but you know, other projects we have looked at the effect of impurities anode side gap. Cathode side, it's obviously very important and to be taken into consideration, but yeah, it's not something that we did here. Would it actually affect the catalyst degradation? It could do. Depends what it is. You know, there are all kinds of adsorption effects that can occur to poison the catalyst, as you know. So yeah, but once again, it's difficult to be precise here because it's not something that we did. But nevertheless, you know, it's in our area of interest. And being done, yeah.
Yeah, and if I can just complement very quickly, also on the side of the infrastructure, we also have projects which are really dedicated to always keep the purity of the hydrogen as it should be. So for example, when we're looking at the different technologies for compression, the purity is always one of the aspects we are considering. And also we have a project now which is actually looking specifically at the purity of hydrogen. So we are doing a sampling of all the HRS that are active right now, and we are really going to measure what is the purity of hydrogen to make sure that it's always as it's supposed to be. So of course we need to know what happens if impurity goes in there, but we try to prevent that, like the same as you wouldn't like to have water in your gasoline when you fill your tank. So.
Martin Lehmann from Mann & Hummel. Thank you for asking that question about the cathode air filters. And Pietro, thank you for mentioning the H2MAC project. And we are looking there as well as the cathode air filter and at purities, and that's a project where we look at the adsorption. So there are some projects, but it's usually a smaller part in these projects to look at. We have some national projects, but it would be a nice, interesting topic for the future. Thank you.
Oh, Simon, maybe I have another question in between. So again, for the cell colleagues, a question. It's a really really the end of project question maybe. So when you look at the results you have for the new materials and the cell stacks and the stacks you developed, in your opinion, when looking at the heavy-duty application compared to the passenger car application, is that heavy-duty application maybe more tolerant towards a slower system response in comparison to a passenger car sector, or did you have different experience here?
I will try. Maybe, well, we didn't, again, not really focus on this specific question, but I would say, yes, focus was road and highway transportation. And with that respect, I would say, I would assume, yeah, that how to say, it is easier to implement our technology, but also in terms of hybridization concepts. And I think this is really important that we have a good operating strategy here. These issues can be solved quite easily, yeah, in using a really good hybridization strategy, yeah. And this is my opinion on that.
Thank you. Just trying to keep the conversation going, especially thinking about the link then from all of the low TRL activities that we've got here and then applying them onto the heavy-duty vehicles. Thank you for MORELife that you're involved now in the Avito cluster. That's very good to hear. Has there been any interaction in relation to StasHH and the Avito cluster? I'm particularly thinking also not about the tractor unit applications, but also the trailer unit applications as well, and the comparison with your boxes, etc.
There has not, but we can fix that.
Yeah.
Good. Thanks.
Yeah, sorry, just one quick question still for you, Federico. So I think you showed at the beginning of the presentation of a rather impressive consortium. You have a big chunk of the market of the fuel cell suppliers and also a heavy participation from the OEM. So we came up with the standards, we are testing now the prototypes. When the project finished, mission accomplished or not? What are the next steps then really to get the buy-in on the industry to make these standards really the standard, to make sure that everybody follow up? What is your feeling also?
Well, I see there is a lot of interest in the industry for the standard. We get from OEMs, we keep getting people sometimes also from other continents say, can we join the project? That's not how it works, sorry. But on one hand, we recently, okay, you don't know, but Pietro is my project officer, and he probably has nightmares with all the amendments I'm sending him. It's a big consortium, there is a restructuring here. In one of these amendments, we added the requirement that all fuel cell manufacturers have to present a public deliverable with a final design. So they cannot hide and say, no, it's not ready. It's going to be ready. It's going to be designed, and it's going to be public. So everyone will see that they can order this at the end of the project. That's going to be, well, there is an amendment running, so it's going to be the end of December. And also one thing we want to do is to set up some sort of permanent StasHH maintenance group based in the industry. It's still a bit hazy idea exactly how we're gonna implement that, but of course someone will have to maintain the standard after the project, but it's a bit early to decide yet.
Hi, I have small questions about the long-term cost-efficient impact between electrification and hydrogen. So do you still think hydrogen can get low cost, because now batteries are actually getting cheaper every day? So in the cost efficiency is going to be better or not?
I can try to answer that. Batteries are, of course, already mass-produced, and there is, I've seen, for example, BNEF's assessment where they have this constant learning rate, which I think is anathema, because it kind of converges to zero, and the cost of battery cannot converge to zero. It can only converge to the cost of the raw materials, and that's a fixed floor. They cannot get any cheaper than that. You cannot get batteries that are cheaper than the materials you built them with. In the case of hydrogen, of course, you have this permanent issue of lower efficiency of fuel cells compared to batteries. Batteries are also heavier. So this efficiency is true for as long as you're not considering the fact that the powertrain has its own weight. And if the weight starts becoming a concern, and that is the case of heavy duty, if you have, for example, it's Tesla Semi, then it's going to have a lot of batteries, and those batteries are going to steal carrying capacity from the rest of the truck, and that can be somewhat tolerable in America, where you have bigger trucks. In Europe, maybe not so much. And in general, you need to look at the whole total cost of ownership. It's true, you get more efficiency for the batteries, but if you can manage to have a decent infrastructure for hydrogen distribution, and it's a lot easier for heavy duty than for light duty, then I believe you have a good business case, the heavier the duty it is.
Thank you to all the speakers. I have a question to Federico for the STASH project. It's quite clear, what could be the benefits of standardization in terms of production and also integrating into the vehicles. Maybe I missed the point, but have you also considered the design of these standardized modules from the LCA perspective, also with regard to recycling, ease of recycling, ease of disassembly?
You did not miss the point because I did not mention it, but we actually were suggested to look more at it in our midterm review. It's not part of the original scope. We'll do something about it. It's not quite clear exactly at which point, but definitely it's a good question.
I guess we had one comment from Guido, or is that already solved? Okay. Any further questions from the audience?
It was just a curiosity for STASH in particular, because I was thinking at the revision of the weight and dimension directive. And I think when you started the project, of course, you basically focused on the standard vehicles. How is it changing for the future? Did you see and did you take into consideration what will change in the next 10 years because the size and the dimensions of the trucks will change?
Short answer, no. Of course, that's part of why we should have an industry grouping that taking care of the standard over the next few years after the project is over.
I suggest you to do so, absolutely. It's important, I think, and it will give you also the speed up to market and to see what could be the future in the specific trucks, because of course this will be the kind of trucks that will be designed in the next 10 years.
Okay, then maybe one question to kind of sum the discussion up a little bit, maybe especially towards the fuel cell colleagues. If you I always remember when writing a application for a project, if I would do the same application again, I would do it a little bit differently than before. So especially for the application in the fuel cell in the heavy-duty sector, when you could reframe your project a little bit, what would be the kind of shift, at least regarding that special application that you have here?
More budget, more testing.
Is that it?
That's basically it. No, for sure. I mean, we kind of bound it in this budgetary framework, right? And data is valuable, and this is the reason why I would consider having a little bit more focus on the testing side. Yeah. So development, for sure, yeah, we have to do all these developments, but testing is really important. This is
my conclusion.
From our side, what we would really have liked to have done wouldn't have changed anything with what we did, but we needed a third iteration of membrane electrode assembly to test in short stacks. There's so much learning that's generated from each of the generations and seeing how it behaves, how the new materials behave once they're scaled up and then submitted to the testing. And we needed a third generation actually to bring that learning finally together, I think, so that we could associate both the performance and the durability. And so that's, yeah, but it would have needed a slightly longer project and a bit more budget. Mm-hmm. But it wouldn't have done it differently. We just needed a bit more time, a bit more money.
So you're asking if I have any regrets? Well, I think more time would have been useful. We started StasHH with the idea of finishing within 3 years, and that would have been fine if everything had just snapped in. One thing we did not account for in the time planning was that we need to align with the development cycle in the fuel cell companies, and that is not something that they are very willing to share at the beginning. And then when it shows up, okay, but we are really going to prepare the new stack 2 years from now, okay, but that's going to be after the end of the project, okay, amendment, and then that's when Pietro starts to suffer. Definitely, this kind of project will need at least 4 years.
Okay, thanks again for all the answers that you had to provide for us. Last chance for the audience if there's one question left. Otherwise, yeah.
Just a very short question. Again, I don't know if it was already addressed. I don't know the details to Federico. We speak a lot about modularity, flexibility, interoperability. Is it somehow considered to also make these fuel cell modules, or at least let's say harmonize the designs with the modularity that we think about when we design battery packs, for example, or battery systems, just so you can have the same dimension of a package fitting into a fuel cell electric or a battery electric vehicle? That's all.
Short answer, yes. And specifically the picture of the truck as shown when they had two A-sized fuel cell modules by Plastic Omnium built at VDL that used to house a battery.
Roland's not looking, so I'll throw in one last question. Just on the StasHH side, just for interest again, you've got your box dimensions. Is there any orientation limit? Can you turn your box upside down and the thing will still run?
You can ask for an upside down box, but then I mean you have liquid water coming out, so definitely orientation, and you have a drain. So we actually consider that the possibility of having a tiltable one, but it can be provided by a fuel cell manufacturer if they want, but that's not part of the standard. But it's possible. Not upside down though. That's not going to work.
Okay, so if there's no more questions left, then again, thanks to all the presentators for the presentations and for having all the questions answered from your side today. So thanks again. Thank you.
Hello.
Okay, good morning from our side and welcome back to the session. We're going to continue the previous session on hydrogen for heavy duty. That was my colleague Pietro before told you about the importance of, and between, let's say, the low TRL development that they were the previous projects that they were presenting. And now we're going to the deployment phase, and which is one step before, let's say, the market upscale and the innovation phase. My name is Georgios Tzamalis. I work in DG Move. I work in the Research Innovation Unit from DG Move. And I'm happy to moderate this session together with Roland from RWTH. And we have actually two projects to present. They're both on the different aspects, equally important. One is on the refueling and the refueling infrastructure for heavy duty. And without further ado, I give the floor to Visan Matler, who works in Toyota since 2007, and with different posts, and currently he's in the Research and Development Fuel Cell Division since 2017, if I got it correctly. And yes, the floor is yours. Thank you.
Okay, so I'm not myself the project coordinator, but I participated in this project, so I will try to do my best to explain the PRHYDE project, which is development of a protocol for heavy-duty fueling. So first, I will go to an overall project presentation. It was normally intended to be a 2-year project, but due to COVID, we had to extend it a little bit, so it became 2 years and 9 months actually. And most of the budget went into testing of our simulation software in real-life situations to check what the tank temperature would do internally at different locations when fueling at high flows. So this was a little bit of a special project because it's not only European project. There were several other companies involved outside Europe. Big thanks to Toyota North America, who assisted a lot into this project, and especially to Steve Matheson from First Element Fuel from California, who also participated in this project. You can also see Nicola, for example. These non-European companies, they participated to this project without any funding. So we know that there was already a protocol available for light-duty vehicles. Most of us are very happy with this protocol. It's actually two protocols. There is a table-based version and an MC formula version for light-duty vehicles, and it's worldwide used all over. However, it was a protocol from SAE, J2601. And it's not really an ISO international protocol or EN protocol. And it's difficult to use SAE into EU regulatory frameworks. So we needed, first of all, to have a more general protocol on ISO level, and also a protocol for higher flows. Obviously, fueling heavy-duty vehicles with the light-duty vehicle protocol would be way too slow. So the overall objective was to support this standardization. And so actually I have to say that the PRHYDE protocol, the result from the PRHYDE project, which is finished already, is not a copy-paste protocol that you can immediately program into your dispenser and you can go ahead with it. It's more laying the foundation stones for developing protocols, because protocol development takes much longer and much more testing than just 2 years. And this was done for heavy-duty vehicle high flows up to 300 grams per second, which is very high, for 350, 500, and 700 bar conditions. So there were a lot of experts involved from Air Liquide, other companies who are very specialized in this and were able to test a lot of these fueling situations. So let's have a look at the results. So as I mentioned, light-duty vehicle protocol already existed, but that was for 2 to 10 kilogram. There was an extra chapter in that protocol where you could go above 10 kilogram. It was called category D, but honestly, this was suitable. It says here 30 kilograms. I would rather say 20 kilograms, 25 kilograms within a decent time. You could go higher, in theory unlimited, but then the fueling time would take so long, it would never be accepted by logistic partners. So there was a real need for it because at that moment with the light-duty vehicle protocol, the fuel speed was only limited to a flow of 90 grams per second. So we wanted to fuel 30 to 100 kilograms, much faster fuel, and all fueling within 10 minutes. That was actually the goal of that. And what was the approach that we took? Well, the current approach from SAE J2601, that was a fueling which was also possible to do even in non-communication mode, because they took from all manufacturers all the thermophysical properties of all different components, and like pipes and tanks and manifolds, receptacles, nozzle, hoses, etc. And they just took the worst case condition of each individual component, and then based on these worst case condition, a protocol was predefined and programmed into the dispenser. So any kind of vehicle could arrive and we could fuel safe. That was the basic intention. But obviously, if you had a vehicle which was much better than the worst case condition, it would result in exactly the same fueling time, and in an end temperature of maybe 55, 60 degrees, while it could go much faster and reach 85 degrees without any problems in a much faster time. So the PRHYDE approach is a bit different. In the PRHYDE approach, there will be a difference between one truck and another truck, for example, even though it might have exactly the same volume, same capacity in the tanks, but maybe truck number A has a much lower pressure difference than truck B, and then truck A will be able to fuel faster which was not possible with the current SAE protocol. And so in this case, it were the trucks that were going to send the information to the dispenser how they are going to be fueled. I will explain you later how this is done. So the PRHYDE protocol concepts offer performance improvements, and yeah, we did several testing, and it succeeded. And the big advantage is also that the OEMs can choose, they can become competitive, and they can say, okay, my truck will fuel much faster than my competitors. And National Laboratory in California, NREL, has a H2 fill simulation software. And we did simulations. We checked the simulations with real-life measurements, and the simulations and also testing has proven that it is possible to do within 10 minutes. The most recent one that I've seen was, I have to remember, I think it was about 89 kilograms in about 9 minutes time. Now, I have to admit, in that case, there was no nozzle receptacle connection. It was a direct connection. So that makes it a little bit different. So but still, the results are quite good. And it's based on the advanced MC formula, which was already existing for light-duty vehicles, but it's an advanced version. So how does it work? First of all, the vehicle OEM, he needs to define a set of what we call T-final tables. Those are tables depending on the ambient temperature and the dispensing temperature. You check what, at these conditions, what should be normally the fueling time under these specific conditions for this specific model. So a special simulation software needs to be developed in order to enter all the data, and then it can develop these T-final tables. And you can have as many T-final tables as you want in your vehicle ECU, and they are stored in the vehicle itself. Then, when the vehicle arrives at the station, it will have a certain temperature, tank temperatures, it will have a certain initial pressure, and it will choose the corresponding T-final table, and it will send that T-final table to the dispenser and telling, hello, I want to be fueled in this way. This is the way I want to be fueled for my truck. This is very different to the current protocols where everything is already pre-programmed into the dispenser, and he will fuel any vehicle at in the same method. So we differentiated different types of protocol. The type 1 protocol, was the one which used no vehicle information, so you can go into non-communication mode, even if you want to. And actually type 1 versions, even based on the PRHYDE protocol, they will also exist. Actually, they already exist because they are now integrated into the new standard SAE J2601-5, which is specifically for heavy-duty vehicles. So that's the first type. The second type is what we call a static type, where a lot of information is sent to the dispenser, but it will not really use the dynamic approach where it is continuously checking the pressures and temperatures of the vehicle. But it will, for example, check if fueling history was present. So, for example, if a truck has fueled first at 350 bar because the price is cheaper, and then afterwards just takes the next dispenser at 700 bar to top off with a little bit more expensive, that will be taken into consideration. And then we have the more advanced versions, type 3, which are called T-gas initial plus, and also T-gas throttle has been developed, where we will take much more into account the initial gas temperatures and also pressures of the vehicle. And with T-gas throttle, this is really a fully dynamic protocol where the fueling continuously depends on the current pressure and temperatures inside the vehicle.
So what are the mid and long-term expected impacts? Well, it is already happening at this moment within ISO Technical Committee 197. Working Group 24 has been established, and there are 3 different standards in that one. ISO 19885-1 is a general standard concerning fueling protocols for heavy-duty vehicles. -2 is concerning the communication between the vehicle and the station. But -3 is about the protocol itself. And of course, those protocols will be used to program the stations. And there is a subgroup 3B, which is called the PRHYDE protocol. It's based, of course, on the PRHYDE project, and it will go further, and it will be able to fuel with very high flows up to 300 grams per second. The hardware is still lacking. There is already hardware for 700 bar heavy-duty fueling based on a 90 grams per second nozzle and receptacles. Those are already existing. But however, within ISO 17268-2, it must be, sorry for the mistake here, this is incorrect. It must be -2. There is the discussions concerning the geometry of the high flow nozzle and receptacle still need to start. So they will start one of these months. So that one will come a little bit later. And then, of course, we have the dispenser communication. It's still a lot of discussions going on in that working group. Shall we go for Wi-Fi, Bluetooth, near-field communication, maybe direct connection like with the electrical vehicle? So this is ongoing. But in the ISO 19885-3, as I said, so there are multiple protocols, and several of them will be based on PRHYDE. So there will be not only subgroup 3B, but also subgroup 3E, which is more on a 90 grams per second, but based on PRHYDE, and also 2 times 90 grams per second as a twin nozzle one. Yep, and as I already mentioned, the -5 is actually already based on, thanks to the work of PRHYDE, is already based on the PRHYDE protocol, but with a difference because we are still linked to the infrared communication. Infrared communication is not yet SIL rated, so that one will have the tables not programmed into the vehicle, but into the dispenser. Then, so landscape is what is contained. It will be about 350 bar, 120 grams per second, is already existing. But yeah, honestly, for CEP Wenger, it's a table-based protocol, but it's very limited, only from 20 kilograms to 42.5 kilograms, which means that if you go above that value or below that value, the Wenger table-based protocol is not applicable. But they can always use the MC advanced MC formula from the -5, because that one goes from 10 kilogram to 7,500 liters. I don't know the value anymore for 350 bar. So from 250 liter tanks to 7,500 liter tanks. That's really a lot, 7,500 liter. So it's not only applicable for trucks, but it can also be used for trains or other applications that are using big tanks. Then we have here the 70 megapascal, 90 grams per second is already incorporated into the -5 as a table-based version, but also it's missing here, also as an advanced MC formula based on the advanced MC formula based on the PRHYDE protocol. And this can be doubled up to 180 grams per second, which is subgroup 3E, as I already explained. And then the fastest fueling will be 300 grams per second, but there you will need different hardware for making this possible. So that was the quick overview of the PRHYDE project. You can always contact me on this email. Thank you.
Thank you very much, Vincent, for your very thorough presentation. I'm sure people will have questions, so you can ask at the Q&A. I'll pass now to the next presentation, and I have the pleasure of welcoming Alex Stewart, who is a partner at ERM and has been working for several years and involved in several EU hydrogen demonstration projects like H2ME, Jive, and of course H2All that he's going to present currently. The floor is yours. Thank you.
Thank you very much. Very good. So, thank you for the invitation to speak. I'd like to present the H2All project to you today, which is an EU-funded project that we initiated and continue to coordinate. So, just very quickly, who ERM is, because you may not know us. I previously worked for Element Energy, which was a low-carbon energy. Effectively, it was a startup back in the day when I joined, and we initiated and supported the majority of the EU demonstration projects alongside lots of other activities in low-carbon energy. Coming up on 3 years ago, we were acquired by ERM, and that's the new name. We've adopted the name. So you may know Element Energy from previous projects that have been presented here and at other conferences. And ERM itself is a very large pure play sustainability consultancy that's building up an energy transition team, partly through acquisition of us and others. And so I'm part of what's called internally sustainable energy solutions that works across low carbon energy, buildings, transport, and hydrogen. And within hydrogen, we've developed this specialism of initiating big demonstration projects and then continuing to coordinate them as they go through their implementation phase. So since probably 2010, European funding bodies, primarily what was the FCHJU, the Fuel Cell Hydrogen Joint Undertaking, which is now the Clean Hydrogen Partnership, has funded increasingly ambitious demonstration projects for a wide range of hydrogen vehicles. So it started, back in the day with the CUTE project for buses, and then Chic and projects for light vehicles, and then the current wave of projects are those that you can see here, that are, some of them are approaching their end, but some of them are still going. So for cars and vans, there's H2 Mobility Europe and Zephyr, so that will deploy by its end 1,400 cars and vans and 50 hydrogen refueling stations across Europe. Zephyr wrapping up at the moment 180 taxis and other vehicles, with the Metropolitan Police in London testing vehicles in intensive use cases. And then on buses, the Jive project deploying nearly 300 buses and HRS in 20 cities across Europe. Again, the latest in a long line of demonstration projects of buses that have now helped commercialize the technology and got those vehicles running reliably, efficiently, with costs now coming down very strongly in the next generation of vehicles. And then H2 Bus Europe still in its ramp up, aiming for up to 600 buses at much lower costs and to replicate the successes of the projects to date across different cities and with increasingly large volumes. And then finally, to get to trucks, the subject for today, H2All is one of the first truck demonstration projects as opposed to R&D projects, and we'll come to that in a minute, deploying trucks from 2 manufacturers. And then that has led directly to a successor project called H2Accelerate, with the participation of Iveco, Daimler and Volvo, which will deploy 150 hydrogen trucks and 8 more stations from the midpoint of the decade. And the H2Accelerate project, I'd argue, is sort of the one before the full commercial rollout, which the truck manufacturers will need to do to meet their fleet CO2 targets in the EU regulation from 2030. So H2 Hall then, it started 5 years ago. These projects always last long, and as Vincent mentioned, with COVID and then some other delays, they have a history of being extended and needing a little bit more time to meet their objectives. So the overall objective is to deploy long haul, heavy duty, so 26 to 44 ton fuel cell trucks that meet customers' requirements in a range of operating environments. So this is not R&D and you know, playing with things on a test track. This is vehicles in service with demanding clients, using their full driving range each day, pulling loads at maximum gross weight, using different refueling stations, and you know, proving to the project partners and of course to the wider logistics sector that fuel cell trucks are viable and present advantages relative to battery electric vehicles in certain use cases, primarily of course ones with high driving ranges, high weights, possibly difficult climatic conditions, where fuel cell will sit quite nicely alongside batteries as another solution for zero emission decarbonised road freight. So these trucks didn't exist, of course, at the beginning of the project. So before you can get them onto the road, you have to design them, you have to integrate fuel cell systems, power electronics, tanks. You have to homologate them so they're legal for use in different European member states. And then, of course, you can deliver them to customers and get them going in the real world use. You need infrastructure to support those vehicles, of course. So in the different sites in the project, refueling stations have been installed or upgraded depending on the starting point, ready to support those trucks as they enter service. And the aim is to achieve 2 million kilometres of day-to-day driving, as I said, in true real-world conditions. And as with almost all of the European projects of this type, there's a strong focus on monitoring and evaluation. First of all, to make sure to the Clean Hydrogen Partnership that the technical criteria have been met and it's justified the 12 million euros of public money that's been spent on the project, for which thank you. And of course, to also make sure that we learn as much as we can from the project to feed back to the project partners to help improve trucks and stations in the next generation, but also to help the dissemination activities to show to fleets that these trucks have been successful, they've met their technical requirements, and they're suitable to be ramped up in the future in a wider range of use cases and a larger group of partners beyond these early adopters. And then there's work on developing the business case, looking at the total cost of ownership, where the most interesting market segments are, and how do you commercialize this technology, starting from, of course, a very low base of these first 16 vehicles. So the partners are those that you see here. We initiated the project and we're doing the coordination. There are 4 deployment clusters in Belgium, France, Germany and Switzerland, with a range of partners that you can see there. The truck manufacturers, there are 2 of them, VDL and Iveco, and we also have the various fuel cell suppliers as formal partners in the project, and then various other partners providing either the HRS and the hydrogen refueling stations, or the truck operators and sometimes the end customers for the vehicles, to make sure that we maximise the availability of the learning and the data generated by the project. So the broad flow of the project is what you can see here. So as I mentioned, there's quite a lot of work to do initially to specify the trucks. You know, what technical characteristics will they need to meet the operational requirements, such as the range, the refueling time, and so on. Of course, comply with length and weight regulations in Europe, and the packaging of the fuel cell systems on the vehicle. When the project started, the truck manufacturers had not yet selected their fuel cell provider, so already that was a step to select those providers and then work on the integration of the systems into the vehicle. And then HRS site preparation, making sure, of course, the infrastructure is ready for these trucks. Then truck deployment, operation and maintenance, which is about to begin. And then, as I mentioned, the monitoring analysis and the dissemination activities that will make sure that we maximise the European value for money and the impact of the project on helping to accelerate the next phase of deployments. So the progress to date, truck specifications and designs have been completed, the prototypes have been built, there has been internal testing of these vehicles to make sure that they're safe and suitable to be used on public roads. The Iveco manufacturing site has been opened during the time frame of the project, and we're now nearly at the end of the truck construction for the 16 vehicles that will be put into service. There's been some hold-ups on homologation, as there often is. Vehicles that were expected in end of 2023 will probably go into service in the first half of 2024. And then they'll need to operate for probably a year or 18 months to meet that 2 million kilometres target for operation, which is one of the technical criteria of our funding. So here are the trucks. So they're both tractor units, a 4x2 tractor from VDL and a 6x2 for the Iveco group. You can see there the fuel systems behind the cab, still leaving space to fit the trailers behind that. So while the vehicles have been are being prepared, the stations have been installed, and in some cases they're already in use by other vehicles developed through other projects, which is why you can see DAF trucks and Hyundais in the top left there, using the H2 energy stations. So in other words, to make sure the stations are in service and they're not sitting idle pending the arrival of these trucks, the stations have been sited and dimensioned to support other vehicles that are either currently in service or will be deployed alongside H2 Hall to maximise the utilisation and the business case, of course, for those stations. We don't have many outputs yet from the trucks, of course, because they're not yet in service. We do have data collection ongoing for the stations that have been put into operation. You can see here the quantities of hydrogen in the blue bars throughout so those are daily average utilisation of stations. So probably 3 or 4 fills per day, depending exactly how empty the trucks are when they arrive. What you can see here is the average speed of dispensing in kilograms a minute, and you can see in that orange line a seasonal trend where the speed goes down during the summer and back up in the autumn and the winter because the cooling requirements of the station change as a function of season, and the speed goes down to protect the maximum internal tank temperature. These numbers are significantly lower than what you've just seen in Vincent's presentation. I think underlines the need for the PRHYDE project and the next wave of refuelling protocols, because if you're at 1.8 kilograms a minute here, even at the maximum, then that's 18 kilograms in 10 minutes. If you've got large tanks of 50 kilos for some of these long-haul trucks, you're nearly at 30 minutes, and that's not going to be acceptable to end users, and is not really a distinguishing feature from a megawatt scale charger for battery electric trucks. So we need the next wave of protocols, as Vincent has described, to reinstate those advantages of very fast refueling, even with the large tanks that you see here. So the trucks are going into service, as I mentioned, but there are also already quite a few learnings from the work done to date. So there's been a lot of work on selection of different refueling pressures to start with, and there are 2 already within this project. So the VDL uses 350 bar and Iveco is using 700. Daimler currently talking about liquids still on the vehicle side, even though the vehicles for H to accelerate will use gaseous refueling. There's been work on selecting the route distances, so the optimum logistics flows to make the best use of the technical characteristics of these trucks. So those are between 250 and 600 kilometers. As the network develops, of course, you could do a lot more than that. You could start doing 1,000 kilometers with refueling at the halfway point. And there's been work to select different emission profiles, climatic conditions, different topography with more or less relief to show that these vehicles can haul things up hills and manage exactly the same quality of service that diesel can provide. There have been some specific trailer requirements in Germany that have had to be met. A change in the plan from a rigid trailer with a drawbar to a tractor unit. So there's still things that need finalising at a regulatory level at member state levels as opposed to the whole of Europe. Same story on some of the divergent planning and permitting procedures, so country and even region-specific permitting procedures for HRS causing delays and costs in deploying those stations, and the need to work very early with the competent authorities to make sure that timelines are respected. We mentioned the PRHYDE project there that's essential for the future of hydrogen trucking. And then work, the lessons learned on the business case. The stations have to be very highly performing. That has not always been the case with light vehicle stations and heavy vehicle stations. There's more of a focus on redundancy and ensuring that there are no single points of failure, because you can't have trucks sitting around waiting for hydrogen if we're going to encourage the next wave of logistics companies to deploy these things. And then, of course, high utilization, an obvious point. High utilization is a critical component for making the business case work. And that's a challenge when, from the OEMs, we expect an exponential type ramp up towards 2030 as they need to meet their targets. So there's a challenge here of building the infrastructure starting from now because of the time required to get this in the ground, but the fact that the trucks will come relatively late in the decade, and other ways to share the infrastructure with other vehicle types, to use captive fleets to carefully align the deployment of the trucks and stations to avoid multiple years of underutilization in advance of the trucks coming. And then, of course, collaboration with other projects is highly valuable. I've listed some of them here, looking at the durability and lifetime of the stacks themselves, standardization of fuel cell modules to simplify integration in the trucks, but also potentially other vehicles related to trucks like coaches and even off-road machinery. And then there's potential for jointly communicating on the state of the sector and the benefits of hydrogen across the different EU projects. I think I've covered most of this. I think the other thing I would mention in the top right here is expectation management. These are demonstration projects, and they're there to go through the teething troubles and learn things so that they can be addressed before the next wave of deployments. We've seen that very successfully in the bus projects, where early in the bus projects the availability of the vehicles was very low, nowhere near diesel, with plenty of breakdowns, often in fact very rarely to do with the fuel cell and the hydrogen components, and often to do with the fact that they were hand assembled in very small numbers compared with the more series production for the diesel vehicles, and that had an impact on availability. And similarly, spare parts weren't widely available. We were flying engineers across Europe to repair things rather than using local technicians. And after several years of observing that and working very hard to rectify it with spare parts placed close to the points of operation, increased training, looking at failure points and improving components, we're now at a stage where the buses are operating very reliably. You never saw that problem with Vincent's Mirais. They've been operating extremely reliably from the beginning, which reflects the fact that global OEMs can just build things in big numbers with extremely high quality control, and the buses are now approaching those levels of reliability. So, to summarise what's going to happen from now on, so the truck deployment is expected in 2024, and the collection of the operational data will start. There's a lot of work to be done collecting that operational data and then processing that, looking at reliability and fuel consumption and some of the technical milestones that we're trying to hit, and then using those data in life cycle cost analysis, looking at well-to-wheels and the environmental performance of the vehicles, and then taking those data and looking at what the impacts are for the next wave of commercialization. Can we identify the segments of logistics where these vehicles make the most sense, the geographies where they make most sense, and how do you then plan the rollout of vehicles and connecting them with the most interested customers to get a business case that works for the vehicles, the hydrogen, and for the end users. Thank you very much for your attention, and thank you for the funding we've received for the Clean Hydrogen Partnership to enable the project. Thank you.
Thank you very much, Alex, for your very thorough presentation. I'm sure people will be interested to discuss these issues, and I'll pass the floor to Roland to kick off the Q&A session.
Thanks for the presentations again and for the nice summary of the two projects. Maybe again, I will start with the first question and then hand over to the audience. Maybe the first question regarding the PRHYDE project. As we know from battery electric trucks, there's quite an intensive communication between the station and the vehicle. Even if it's a car or it's a truck, they have quite a good exchange protocol. You proposed some next steps for future protocols of hydrogen refueling. Maybe it's even two questions. Which protocol do you think is the next one that really comes into application? And what is the big obstacle in the way for the communication right now? Why is there a need for this T-final tables, and why do not exchange data directly from vehicle to station?
Okay, those are two questions.
Yeah.
Let me start with the communication question. So in order to enable PRHYDE to work properly, you will need bidirectional communication, which needs to be trusted, 100% trusted. So that is for sure. If you don't have that one, maybe there is another good chance that we can fuel 100 kilograms in less than 10 minutes. Because then you will stick to the protocol which we are having now in SAE with the -5, which is already not so bad. Honestly, it's performing quite well, but it's not what the target is yet. But as I already mentioned, these discussions are already continuous in the ISO, and there is not yet any decision made on how this communication will look like, but it is absolutely necessary. And then the second question was?
The second question was basically regarding your three types of communication protocols, so real-time application and these T-final protocols. Which one do you see next coming up, basically? Is it still calculating on the vehicle side, or even exchange information already?
Yeah, maybe I'm a bit biased, but I think the -5 SAE will, for the next years, will be the real standard that everybody will start to use, because it's already available. You can immediately use it in your dispenser. So we will have to wait for the ISO protocol to be published, or at least the draft version to be published, before station operators will start to integrate this. The Japanese, they have already started last summer using actually the Dash 5. It was a table-based version, but it doesn't matter which one it is. But using with the two light-duty vehicle nozzles, and they were able to achieve at 29 degrees ambient temperature 60 kilograms in less than 10 minutes. So that way it is possible, and you could then, for example, use a light duty vehicle dispenser which can fuel two Mirai simultaneously, also for fueling one truck. So that technology could be implemented already today, and then you can fuel very, very fast. For the 300 grams per second, we will have to wait a little bit. So it's a bit guesswork when the hardware and protocol will be finished.
Okay, thanks for the answer. So maybe now for the audience, feel free to just raise your hand if you have any questions.
Thank you again to both the speakers. I'm not really the expert, but this is particularly to PRHYDE project. I can imagine that there is some influence of the storage technology itself and the capacities. Is this something that's also taken into consideration for the different protocols?
Yeah, so this is part of the communication, but actually this can also be done with the current infrared communication, where we can explain what not only the total tank size is, but also, for example, the individual tank size could be transferred to the dispenser, and this is taken into account into the protocol. I'm not sure if that is an answer to your question.
Different types of storage technologies, right? The mechanism by which hydrogen is stored, right? Does this have any influence?
You mean like type 3, type 4, yes, and so on. That is in the PRHYDE protocol, it is foreseen because it's all included into those T-final tables. Yeah. So type 3 tank will be able to fuel much, much faster than a type 4 tank, for example. Yeah.
A quite simple question. Are these new protocols that are about to be established, are those completely future-proof? So are those, I would call them flow rates that you are referring to, will they be sufficient even in the next 5 or 10 years, or is this like very speculative? I'm not an expert on the topic, but I was just wondering how what kind of advancements needs to happen in order to have wide deployment in the next years, basically.
Yeah, it has been the target from the very beginning of the PRHYDE project to achieve diesel parity. So if you can fuel 100 kilograms in less than 10 minutes, then you achieve diesel parity.
Further questions? We have one over there.
Also for within the PRHYDE project, would there also be some sort of error detection in the future in place for refueling? So let's say you have some sort of, well, leakage or that kind of stuff, where indeed, especially dynamic way of refueling, so less based on the T-final maps, where you could use those sensor data to detect something that is not going right or something like that, so more of a fail-safe.
That was the smart tank concept or leakages and so on. That was not part of the scope of the project.
Okay, maybe I have a question for the H2O project, just to have at least some parity here. So in the session before, we have heard a lot about the degradation of the fuel cells. And when thinking about your project being such a huge application project, will that be part of your investigation later on when the trucks are in operation, how the use case kind of influences the degradation?
Yes, it will be. I guess there's a question about how much degradation you see in the 1 year or 18 months of the project. But yes, certainly it'll be tracked. Some of it summarized at a public level, but certainly at the OEM level, they'll be collecting efficiency data and all the voltage data and things that you need to track that degradation. So far, I don't think it's been a huge problems in the vehicles we've seen so far. In the buses, there are DC-DC converter problems that impact the reliability a lot. I've not seen too much about degradation of the stacks themselves, but I guess, like everything, the vehicles, the highest number of vehicles are the most recent ones because it's on a curve and they haven't yet seen 5, 7, 8 years of service.
Okay, so we have another question.
Okay, so again, it's about H2 Hall, just to keep some balance again with the questions. So we're talking about this degradation. I would like to ask you, do you have any particular goal of the track availability? What are you aiming at?
I'm not sure if the availability is a metric that's tracked. It certainly is that it's tracked. I'm not sure it's the technical criteria of the call. The expectation, just like the refueling speed, is diesel parity. For the buses, I think we've got to from 60 or 70% very early in those projects through the teething problems through to 95, 99% availability. And that's where the trucks will need to be certainly at 99% or better to be competitive. I don't expect that from the first few months of operation of 2 completely new vehicles, to be completely clear. But that's why we do the projects, and the expectation is to equal diesel. In theory, these vehicles have fewer moving parts and less brake wear and fewer things to go wrong. Once they're made at scale and the QA is as tight as it is for other technologies. But I think we've started to see that with battery electric solutions now. You're seeing the benefits of that simplicity translate into reliability, and no reason why you shouldn't see the same for fuel cells, but possibly not with the first vehicles that come off the line.
So if there are,
I have another one.
I have another one as well.
Yeah, if there is nobody else.
So we will just have questions in front here. Maybe we have one from the audience again.
Okay.
Thank you. Daniel Sütz from RWTH Aachen. I have a question to PRHYDE again, because you talked about how the new standards are in development right now, specifically for communication. So what I would like to ask is, how much potential do you see in just copying some things from the battery standards? For example, plug and charge, and let's call it plug and dispense for hydrogen. How much potential do you see there for just, take work that has been done and adapt this for hydrogen?
Why not? That's one of the proposals in this working group, to use exactly the same communication methodology as for electrical vehicles, and for example have electrical connection, the same type, exactly the same as on the nozzle, which performs according to the same protocol and as for electrical vehicles. Mm-hmm.
Okay, then I will have another question from my side. Just maybe out of your experience, as you have some stations always already available for the refueling of the fuel cell trucks, do you see at the moment already a competition for the clean hydrogen that we have? And especially when thinking about the rollout phase, there will be even more competition with other industries for the clean hydrogen available. And in your opinion, is that already a problem for you to get the hydrogen, or will that be in the future?
That's a very good question. What we've seen with the hydrogen refueling stations is a trend from small stations, often with on-site electrolysis, because the volumes didn't justify moving hydrogen around, through to what's normally called semi-centralized. So we're not talking about a huge SMR plant 1,000 kilometers away, but an electrolyzer at the multiple megawatts scale, connected hopefully directly to the renewables, delivering in a radius of 100 kilometers or so. and the trucking emissions for the delivery are minimal compared with the savings from the use in the fuel cell, and you can access lower electricity costs and so on. So far, those chains have been separate from what's going on in industry. So in that sense, there's no competition. It's often the same actors, but it's not the same projects that are supplying those mobility solutions and industry, which often needs in the hundreds of megawatt scale. We're now starting to see a combined production that will serve multiple end uses, because, as I mentioned, the exponential ramp up of hydrogen towards the end of the decade is really difficult to manage through in terms of underutilization. So the project promoters are looking at ways you can find base load from industrial applications and then either have mobility as a small but growing part of your mix, or have something that you can scale and increase the capacity for the same site. The Shell Holland hydrogen project is a good example of that, where 100% of that output will just go into the refinery. It's complete self-consumption to decarbonize the hydrocracking and the grey hydrogen currently in the refinery. But as the mobility ramps up, then you can either increase the capacity or divert some of that hydrogen back into mobility uses directly to the stations.
I can maybe also add. Maybe I can add something to that concerning competition, and I already explained just a while ago. In Europe, we are really front runner. For hydrogen production and electrolyzers, there is no area in the world that has so many companies involved in developing these technologies, and also for stations. So there are more than 30 station manufacturers in Europe, and they are exporting to Korea and Japan and California, all over the world, and this is really a very big asset, and it's very good to see that there are so many companies seeing a business case into these technologies. Let's hope we can keep it this way.
Okay, I have a question on H2All. So you mentioned about the charging speed that you currently have is 1.8 kilograms per minute, or something like that?
Yeah.
So for 50 kilograms, you need about 30 minutes. Now that you are going to go to the, let's say, to the deployment of the trucks, do you plan to use some of the knowledge developed from the PRHYDE project in order to go to, let's say, to reach faster charging speeds, or?
Yeah, absolutely. So the caveat with the charging, the refueling speeds I showed there is those are for vehicles with smaller tanks in the range of 15 or 20 kilos per fill. So at those speeds, you're back to the 10 minutes or so that's acceptable to users for those tank sizes. But those are current generation stations using effectively the worst case that Vincent described. So that will not suffice for 50 kilos, 80 kilos with multiple tanks and so on. And the PRHYDE learnings will certainly be implemented in that when they're standardized. The slight concern I have is the timescales, because there are stations being funded by this project, by the Connecting Europe facility, for example, with deployment targets in 2024, 2025. Equipment has long lead times. It has to be ordered a year in advance often. And there's a risk that the first wave of large stations that are capable of refueling lots of trucks and will have pride of place on the TNT network will not actually be capable of refueling quickly enough to assure a high quality service. And if truck users can choose between a recent station with the PRHYDE protocols or whatever they turn into versus something built 3 years ago that's slower, then they can choose where they refuel, and that station will see no customers. I don't know, Vincent, if you have a view on how retrofittable some of those things are. If it's about compressors and the flow rates through the refrigeration system, you just have to change a station. But could you imagine stations going in now where the compressors and everything else is dimensioned well, but you just need to add that intelligence and communication at the nozzle end and in the dispenser to then unlock a fast refueling rate?
Expanding extending the capacity. That is for sure possible at this moment, and until you go to very large capacities where you're going with the direct compressor fueling. Of course, then you change the concept of your station. But as long as you add capacity, it should be possible. For the fueling speed, however, if you want to go to high flow, you will need a completely new dispenser with heat exchanger, flow regulators, everything that is able to cope with those high flows. Yeah.
Okay, maybe giving the chance to the audience again for a follow-up.
Andreas Stauder from the Austrian Ministry for Climate Protection, Environment, Energy, Mobility, Innovation, Technology. I'm responsible for vehicle technology development funding at the ministry, and therefore, of course, my interest is in mobile applications. But nevertheless, we have a national hydrogen strategy, and with this respect, as we are responsible for energy policy as well and environmental policy, there is a clear, let's say, statement that hydrogen has to be focused on fields which really need hydrogen, like, for example, in the steel industry and so on. So my question to you is, let's say, is hydrogen fuel cells something what for freight, especially for freight and heavy-duty vehicles, is really necessary and, let's say, without any alternative, or are batteries doing the same job? I mean, there are many advancements with batteries, but nevertheless, the standard ideology was that for small vehicles and short distances, batteries are good, but that for long distances and heavy duty, you need hydrogen fuel cells. So what is your opinion on that?
Yeah, now I'm going to speak from Toyota Motor Europe, not from the PRHYDE project. We are a very big global company, so we bet on everything because there will be regions in the world that want different technologies than other regions. So we think everything is needed, most specifically more for Europe. They both will exist. In some situations, you will have customers who will be very happy with having a battery electric truck, for sure. But there will be also many customers that really would prefer to have a hydrogen truck, and mainly because of the fueling speed. And that will be the most important aspect. We can see the same with buses. Hydrogen fuel cell buses are more expensive than battery buses. Everywhere, but still there are bus operators that have maybe already a certain range of battery buses, but they also want hydrogen buses. There is a reason for that. It could be flexibility, it could be lack of space to put a charger for every battery bus if he has 50, 60 buses, and he prefers a station which takes much less space for fueling a number of buses. There are many different variety of customers, so there will be a variety also in the applications. And actually the same is true for passenger cars, by the way. We know that the minority will be fuel cell, but or light duty vehicles in general. I'm also talking about vans and pickups and so on. Maybe the majority might be battery, but there will for sure also be customers who would like to have the advantages of the hydrogen fuel cell. So it's not one or the other.
I think I completely agree with what Vincent has said. Specifically in heavy-duty mobility, there is within heavy-duty mobility, there is a kind of very theoretical model where you can run a battery electric truck 4.5 hours, for example, until the mandated break, and then you arrive at a megawatt scale charger, you charge 45 minutes during your break, and then you do the next 4.5 hours. And if that works, you never need hydrogen, right? Your limitation is the human at the wheel, and off you go. But it requires no queuing for the chargers, because otherwise you're having a break and then wasting time while you're still queuing. It requires megawatt chargers everywhere with sufficient thickness of cable to bring all that power to the stations, which is equivalent of tens of megawatts that you'd be putting into trucks at an average truck stop. And then you've got other vehicles that don't just go trunking up and down motorways, and they do things in rural areas and hills and elsewhere, and forestry operations and so on. Exactly. So I think you will need both technologies, and we've seen with the buses, a very good example is Gatwick Airport for buses. They've recently installed a liquid logistics hydrogen refueling station, so the hydrogen is gaseous when it goes into the vehicles, but the delivery and the storage on the site is liquid. And when you look at the footprint of that station that can do 140 buses, it's tiny. The efficiency of space compared with reinforcing the grid and having one sufficiently powerful charging point per bus, it's very impressive. And the liquids, of course, reduce the number of truck movements you need to supply the stations. So I think for places like that, for buses, but also for trucks, there will be place where you just cannot reinforce the grid and deploy the sufficient infrastructure, and that's where the hydrogen will work. But even the biggest hydrogen fans, I think, would say, if it works with batteries and the battery infrastructure, then you should do batteries, because the energy efficiency of the chain is better, the operational costs will almost always be lower if you can make it work for you. But that won't be always the case.
Okay, maybe a final question from the audience? Or we are due? Okay. Okay, so then we are done. Thanks again for all the questions.
Thank you all.
Thank you.